So let's for just a minute go back to Algebra 2. When we had 3 variables in our system, what we had to do was figure out a way to solve, right? So we worked backwards. Once we got that one of the variables was equal to something, so for example, here we say that z is equal to 2, I can take that 2 and I can substitute it in place of z and solve. So that's going to give me y plus 4 times 2 is equal to 7, and that gives me y plus 8 is 7, or I'm going to get -1 for y. Once I know that z is 2 and y is -1, I can plug both of these in here and solve for x. So I'm going to have that x minus 2 times -1 plus 3 times 2 is equal to 9. That gives me x plus 2 plus 6 is equal to 9, x plus 8. We are going to get x is 1. And then finally, my system is 1, -1, 2. That's the solution. So using something similar, we're going to attempt to get it in this special form where it's really easy to use back substitution. We see we have a 0 here. We have a 0 here and here in the second one. So that's kind of our goal. If we can sort of make what we are going to call this special form eventually as is echelon form, where it's this sort of ladder going on, that's going to be our end goal because it's going to make it a lot easier to solve these problems. All right, so what we can do is take this same system. Eventually, it brings us down to the same places up here. We're going to take this system and turn it into an augmented matrix to start. So again, any zeros we'd plug in, we've got 1, 1, 1 there. So 1, -2, 3, 9, -1, 3, 1, -2, 2, -5, 5, 17. Okay. So what we want to do is perform some row operations to start to get things to cancel out. Think like elimination in Algebra 1. So if things are the same number, but different signs, that's kind of our goal. We can add them together to get them to cancel. So just like up here where I have this 0 space going on here, if I could somehow turn this into a 0, that would really be helpful for us. That would mean I only had a y and a z in that line. So if I do that, we're going to have, let's see, we could add the first row to the second row. All right, so let's take a look. First row is going to stay the same. Third row is going to stay the same for now. And we're going to add the first row to the second row. So row 1 plus row 2, and that should start to cancel some things out. So if I add 1 and -1 together, I get 0. -2 and 3 gives me 1. 3 and 1 gives me 4. And 9 and -2 when I add gives me 7. Okay. So far so good. I'm starting to get that sort of step going on. Now, if I could turn these guys into zeros, that would be even better to match up here. So let's focus on turning that 2 into a 0 first. Well, in order to turn that 2 into a 0, I'm going to need to add something, right? So let's leave the first row we're happy with. The second row we are now happy with. We need to fix that third row. All right, well, why don't we take the first row and let's see if we're going to add that to the third row. That's not going to quite cut it. If we add it to the third row, that'd be adding 1 and 2 together. It'd be really great if this was a -2 though. So why don't we multiply the first row by -2 and then add it, just like we would with elimination. So 1 times -2 is going to give me -2, and then I add and get 0. -2 times -2 is going to give me 4 plus -5, I'll get -1. 3 times -2, that's -6 plus 5, so -1. And 9 times -2 is -18 plus -17, or positive 17 is going to give me, again, -1. All right, we're looking pretty good here. Now we need to get that -1 here to cancel out into a 0. So first row, again, happy with, totally fine. Second row, we're happy with, we've got that first 0. So far, so good on that third row. We just need to keep going. So we can take the third row, and to it, we're going to have to add another row. Well, we want to make sure the x doesn't show up again. So we don't want to use the first row, because if I add with it, the 1 will then, show up. I'm going to take the second row. Now, if I add the first or the second and the third row together the way they are, they're actually going to cancel. So 0 plus 0 is 0. 1 plus negative 1 is 0. 4 plus negative 1 is 3. And 7 plus negative 1 is 6. Last step, and then we can go back to back substitution. That bottom row, it'd be really great if instead of 3, that was a 1, because that would mean that z equaled whatever's on the other side. Right now it says 3z equals 6. Yes, I know we know how to solve that equation, but this is more for practice. So if I were to multiply that bottom row by a third, that should take care of it. I'll get a 1. 0 times a third, 0 times a third, 3 times a third, 6 times a third. And there we go. So now we basically have the system we had before. That's 1x minus 2y plus 3z equals 9, 1y plus 4z equals 7, and 1z is equal to 2. Or I don't really have to write those ones if I don't want to. So there we have it. And now from here we can use back substitution, just like we did up top. Okay, and we actually had the same system at that point. So we got, what did we get? 1, negative 1, 2. Okay. A matrix in row echelon form has the following properties. So any rows consisting entirely of zeros are at the bottom. For each row that does not consist entirely of zeros, the first non-zero number is 1. We call that the leading one. And for two successive non-zero rows, one after the other, the leading one in the higher row is further to the left. We see this pattern in the example just before this, where we have this stair step going on where we have leading ones. Okay. Now, if we have reduced row echelon form, to be reduced, anywhere there is a 1, all the numbers above and below it are zeros. So, for example, in reduced row echelon form, well, we'll see that down here, we're looking for the 1 to have only zeros below or above it. But that has to be true for all of our ones. Okay, so we want to determine whether each matrix is in row echelon form or if it's in reduced row echelon form. And what echelon really just means, it refers to that stair step pattern. All right, so in this first one, we see that stair step going on where there's only zeros underneath the stairs and ones on each step. Okay, that makes this row echelon form, but it is not reduced. And it's not reduced because above this 1, we have a 2. We have 0 on the bottom, but we have a 2. And above this one, we have some numbers as well. All right, let's look at B. I do not have row echelon form here because the row of all zeros has to be at the bottom. So this is not, it's not either one of these. It's none of these. All right, and C, we do technically have that stair-step pattern, even though we don't have a 1 in that first column, we do have a stair-step pattern here. And we can actually, all right, so we have that stair-step pattern, so hang on one second. So this is a row echelon form. It's not reduced, though, because we have that number above the 1. Let's look at D. We have the stairs, perfect. It is row echelon form. The question is it also reduced? Well, with this one, everything is 0. With this one, 0, 0, good. With this one, zeros and zeros, yeah, this is absolutely reduced row echelon form. Okay, let's look at E. So E is not in row echelon because of this 2. If this 2 was a 1, I'd be in good shape. So this is neither one of those. It's none of those. And then in F, our first one, we make that stair step, perfectly fine. Is it reduced? Well, under the 1 is all 0, 0, 0. Yeah, this is reduced row echelon. Okay.